In this video, we'll be factoring high-degree polynomial functions. We're going to be applying several techniques to accomplish this goal. So given p of x equals 2x to the fifth minus 5x to the fourth minus 5x to the third plus 25x squared minus 7x minus 10, we're going to start by using Descartes' rule of signs to determine the possible combinations of positive real zeros, negative real zeros, and imaginary zeros. Then we're going to use the rational zero theorem to determine possible rational zeros. We're going to use our list of possible rational zeros and Descartes' rule of signs, and then we're going to start testing those possible rational zeros and ultimately write our polynomial function as a product of linear factors. Let's start by making the chart for Descartes' rule of signs. There are positive real zeros, negative real zeros, and complex zeros. To determine our options for positive real zeros, we need to look at the number of sign changes in p of x. So how many times do we change from plus to minus or minus to plus? So there's 1, 2, 3. Our first option for positive real zeros is 3. Descartes' rule of signs tells us it's either equal to the number of sign variations in p of x or less than that by a multiple of 2. If I subtract 2 from 3, I get 1. 1 is a good number for a quantity. We just want to avoid negatives. So 1 is my second option. Subtracting 2 again, I get negative 1. Negative 1 is not a quantity that makes sense. So we have two options, either 3 positive real zeros or 1 positive real zero. For our options for negative real zeros, we need to look at the number of sign variations in p of negative x. So we find p of negative x by plugging negative x in for x and then simplifying. Remember, there is a shortcut. From p of x to p of negative x, all you need to do is change the sign of the odd degreed terms. So the odd degreed terms here are these 3. If I change the sign of those 3 and keep the other 3 the same, that'll be my p of negative x. So this is going to be negative 2x to the fifth minus 5x to the fourth plus 5x to the third plus 25x squared plus 7x minus 10. Now let's look for sign changes. There's 1, 2. 2 sign changes, that's my first option for negative real zeros. But it could be less than that by a multiple of 2. If I subtract 2 from 2, I get 0. Is 0 a quantity that makes sense? Yes. I could say, I have 0 milk. That makes sense. It's just the negative numbers that don't make sense. Subtracting 2 again from 0, I get negative 2, and there's that negative number that doesn't make sense for a quantity. So I only have 2 options for negative real zeros, 2 and 0. To make our chart, we want to do every possible combination of positive real zeros with negative real zeros. We know that our chart is going to have 4 rows, and the way that we know that is you take the number of options you have for your positive real zeros and multiply it by the number of options you have for your negative real zeros. They each have 2 options. 2 times 2 is 4. my chart's going to have 4 rows. And we want to do every possible combination. This is not foiling, but that's what I think of every time I do it. So we're going to have 3 with 2, and then 3 with 0. And then we'll have 1 with 2, and then 1 with 0. We will fill in our complex column. We know that each row must add to be our degree, which in this example is 5. So we just need to figure out what number we would have to add so that each row is 5. Our first row, we already have 3 and 2. So we'd add 0 to that to make 5. Next, we have 3 and 0. We'd have to add 2 to that to be 5. Next, we have 1 and 2. We'd have to add 2 to that to be 5. And lastly, we have 1 and 0. We'd have to add 4 to that to make it 5. Recall that your complex zeros come in pairs, so I always just double check and make sure that that last column is all even numbers. So what information can I gain from this chart? Once I get my list of possible rational zeros, what kind of numbers should I choose? Well, we want to avoid the column that has zeros in it. Notice that negative real has zeros in it. So once I get my list, I recommend we start by checking positive real zeros. All right, let's get our list of possible rational zeros. We know all the factors are plus or minus. We need the factors of the constant divided by the factors of the leading coefficient. Starting with the constant, 10, our factors of 10, 1 and 10, 2 and 5, and then our factors for 2, just 1 and 2. Let's simplify this into a readable list. Plus or minus divided by plus or minus ends up in a plus or minus. So I'm going to start with the first number in the numerator, take it over both the numbers in the denominator. Then I'll move on to the second number in the numerator, take it over both numbers in the denominator, and so on. So 1 over 1 is 1. 1 over 2 is a half. 10 over 1 is 10. 10 over 2 is 5. 2 over 1 is 2. 2 over 2 is 1, which is already on the list, so I'm not going to repeat it. 5 over 1 is 5, also on the list, so I'm not going to repeat it. And then 5 over 2 is 5 halves, not on the list. So here's our list of possible rational zeros, plus or minus 1, 1 half, 10, 5, 2, and 5 halves. Now it's time to start checking from our list of possible rational zeros. My chart from Descartes' rules of signs tells me that I should check positive numbers to start with. I like to always check 1 first. Recall the shortcut that I mentioned about testing 1 using remainder theorem. To test whether 1 is a 0 or not, all you need to do is add up the coefficients of your original polynomial. I always like look at the negatives together and then look at the positives together just to help me with my addition. So that's going to be a positive 27, and then 5 and 5 and 10 and 7. That's a negative 27. So I got positive 27 minus 27. That's going to give me 0. Remainder theorem tells me a remainder of 0. Therefore, 1 is going to be a 0. Well, great. Well, that's the first one I'm going to test then. We're trying to rewrite our polynomial as a product of linear factors. That's our ultimate goal. So we're going to use synthetic division and divide to get it into all the factors. I know 1's going to work, so I'm definitely starting with 1. Synthetically dividing 1 in. Put the coefficients of our p of x. And synthetically divide. And we get the remainder of 0 that we're anticipating. This confirms that 1 is a 0, and since we have a 0, we can get a factor. Starting to factor p of x. If positive 1 is the 0, then x minus 1 is the factor. We divided a 5th degree by a 1st degree, so our next factor is going to be 4th degree, and we get the coefficients from the bottom row of our synthetic division. 2x to the 4th minus 3x to the 3rd. Starting to factor p of x. Since 1 is a 0, we know that x minus 1 is a factor. P of x was 5th degree. We divided it by a 1st degree, so our next factor is going to be 4th degree. And we get the coefficients from the bottom line of our synthetic division. So p of x equals x minus 1 times 2x to the 4th minus 3x to the 3rd minus 8x squared plus 17x plus 10. Next, we need to break down that 4th degree factor, and we'll try to by finding another 0. We're just trial and erroring our list of possible rational zeros. Descartes' rule of signs recommend that we check positive numbers. We checked 1 and it worked, so let's try another positive number. Let's try 2. And we'll divide it in. I did not get 0. I got 20. So this tells me that 2 is not a 0. But let's look at that last column there. I had 10 and 10 equals 20. If I had 10 minus 10, it would have been 0. My gut is just telling me that I should try -2. Even though the chart said start with positives, that doesn't mean that you have to stick with positives. It's just a guideline. That 10 and 10 is so close, my gut's telling me to try -2. So let's try -2. Doing our synthetic division. How nice. We end up with a remainder of 0. A remainder of 0 tells us we have another 0, and if we have another 0, well, then we have another factor. Let's continue to factor p of x. So we have x minus 1. This 0 of negative 2 gives us the factor x plus 2. And then our third factor, it's going to be cubic, right? Because we had a fourth degree that we divided by a first. It's going to be cubic 2x to the third minus 7x squared plus 6x plus 5. When you have a factor that has 4 terms like this cubic, remember that you have other factoring techniques other than just checking zeros. 4 terms, we have the factoring technique of grouping. So if I was doing this, I would definitely see if this was groupable. It ends up to not be groupable, but it's worth a shot. So once you get down to 4 terms, try to group it. Sometimes it works. All right, let's recap what we have here. We have 1 positive 0 and 1 negative 0. Going back to our chart, since there is a negative real 0, that means these two options are out. These options that had 0 negative reals are out. My chart tells me then if there is 1 negative real 0, there must be a second negative real 0. So I would turn my attention to negative real zeros. What's left in my positive real 0 column is 1 or 3. Well, I've already found 1. It's a 50-50 chance that that's the only one it's going to be. With the negative reals, I'm guaranteed a second one. So I would switch to negative numbers. So let's check a negative number. And we just need to pick one from our list. Let's try negative 5. And we're putting that into our third degree factor. And we have a remainder other than 0. So this is definitely not a 0. But I can gain some insight from this answer. My upper and lower bound rules. Here we're checking a negative 0. So C is less than 0. Our lower bound rule says that if you are dividing by a negative, and your bottom row alternates between positive and negative numbers, then this number that I was testing is a lower bound, telling me that I should check numbers larger than negative 5. So let's take a number from our list that's larger than negative 5, but still negative. Let's try negative 1/2. Synthetically dividing. All right, we get a remainder of 0. This tells us that negative 1/2 is a 0, and that 0 gives us a factor. So we continue to factor p of x. Our first two factors were x minus 1 and x plus 2. Now this 0 of negative 1/2 gives us a factor of x plus 1/2. The next factor is going to be quadratic because we were breaking down a cubic. 2x squared minus 8x plus 10. Once the largest factor you have is quadratic, you don't have to check zeros anymore because we have so many techniques for dealing with quadratics. The first thing I would do is try to factor this by traditional methods. I know that there's a GCF of 2 that I could factor out, so let's do that. Monomial factors go in the front. That's x squared minus 4x plus 5. I try to factor that quadratic trinomial further. Unfortunately, I can't think of two numbers that multiply together to give me 5 and add together to be -4. This isn't factorable by traditional methods. So what we're going to have to do to deal with this is find the zero using quadratic formula, and then work backwards from the zero to the factor. All right, let's solve this by quadratic formula. So x will be -4 plus or minus the square root of -4 squared minus 4 times 1 times 5 all over 2 times 1. X will be 4 plus or minus the square root of 16 minus 20 all over 2. That'll be 4 plus or minus the square root of -4 over 2. Well, that's the same as 4 plus or minus 2i all over 2. We want to simplify the fraction overall. I recommend you break it up into 2 when doing that. It's going to be 4 over 2 plus or minus 2i over 2. We end up with 2 plus or minus I. Two complex zeros, x equals 2 plus I and x equals 2 minus I. To get the factor from the 0, all you need to do is set it equal to 0. So for the first one, we'll subtract 2 and subtract I from both sides. That gives us x minus 2 minus I equals 0. So this right here is our factor. With our other one, again, we'll set it equal to 0, so we'll subtract 2 and add I from both sides. This gives us x minus 2 plus I equals 0. Here's our second factor. All right, let's put it all together. Factoring p of x. P of x is equal to 2 times x minus 1 times x plus 2 times x plus a half times x minus 2 minus I times x minus 2 plus I. And that's our final answer. We've rewritten our polynomial function as a product of linear factors. Just to bring our attention back to our chart, notice that we ended up with this option right here. We ended up with 1 positive real zero, 2 negative real zeros, and 2 complex zeros.